Hello, and welcome to Sleepy Facts with Justin. Tonight, we're going to take a gentle journey through space and the universe. A quiet exploration of the cosmos that surrounds us. There's no need to stay alert or remember every detail. This is simply time for you to rest, to let your mind drift like a distant star, moving slowly through the peaceful darkness of space. Over the next few hours, we'll float through the vastness of the universe together. We'll visit distant galaxies, pause beside quiet nebulae, and consider the gentle forces that shape everything we see. The universe is so vast, so ancient, and so calm in its rhythms that it makes a perfect companion for sleep. Out there, beyond our atmosphere, time moves differently. Stars burn for billions of years. Light travels for eons. And in that great expanse, there is room for everything, including your need for deep, restorative rest. So settle in. Let your breathing slow. Let your body sink into comfort. And know that it's perfectly fine if you drift away before we finish. The universe will still be here, and so will this voice, keeping you company in the darkness as we explore the quiet wonders of space and the universe. Let's begin our journey now, drifting outward from Earth into the soft embrace of the cosmos. When we think of space, we often picture stars and planets, bright nebulae, and swirling galaxies. But the truth is that most of the universe is empty, beautifully, peacefully empty. Between the stars, there is darkness. Not the darkness of a closet or a moonless night, but a darkness so complete, so pure, that it has existed unchanged for billions of years. This is the quiet heart of the cosmos, the stillness between all things. In the space between stars, there is almost nothing. No air to carry sound, no dust to scatter light, just vacuum stretching outward in every direction, farther than we could ever travel. And in this emptiness, there is a kind of serenity. The universe doesn't rush. It doesn't hurry from one event to another. It simply exists, vast and patient, allowing everything to unfold in its own time. Light travels through this darkness at incredible speed, crossing distances we can barely imagine. Yet even at that speed, light from distant stars can take thousands, even millions of years to reach us. When you look up at the night sky, you're seeing ancient light. Photons that began their journey long before humans walked the earth. They've been traveling through that quiet darkness all this time, undisturbed, until they finally reach your eyes. The space between stars is not truly empty, of course. There are molecules there, scattered so thinly that you might find only a few atoms in a volume the size of a room, hydrogen mostly, the simplest element, the building block of stars. These atoms drift through the void, sometimes for millions of years, before they encounter anything else. There's something calming about imagining these tiny particles floating alone through the darkness, part of the universe, but not bound to any particular place. Sometimes these atoms gather together, drawn by gravity into clouds. These clouds are still incredibly thin compared to anything on Earth, thinner than the best vacuum we can create in a laboratory. But in the vastness of space, even these thin clouds are significant. Over time, over millions of years, they can collapse and form new stars. But that process is slow. So slow that if you could watch it happen, you'd see almost no change from one human lifetime to the next. The darkness between stars is also incredibly cold. Without a nearby star to provide warmth, the temperature in deep space drops to just a few degrees above absolute zero. That's about minus 270 degrees Celsius. At that temperature, atoms barely move. They drift in near perfect stillness, waiting in the cold and the dark. It's a kind of cosmic hibernation, a deep sleep that lasts for ages. But even in this cold darkness, there is beauty. When light from distant stars does pass through these regions, it creates subtle patterns. Sometimes the light bends around massive objects, warped by gravity in ways that Einstein predicted. Sometimes it scatters off the few dust particles that exist, creating faint glows that telescopes can detect. These are called reflection nebulae, and they're like gentle echoes of starlight soft and diffuse. The emptiness of space also means that things can exist there undisturbed for incredibly long periods. A rock floating through interstellar space might travel for billions of years without hitting anything. It might pass by stars, feel the tug of distant galaxies, but never actually collide with another object. It's a lonely journey, but also a peaceful one. No friction, no resistance, just smooth, eternal motion through the void. This emptiness is part of what makes the universe so stable. If space were crowded, if stars were packed closely together, the universe would be chaotic. Collisions would be common. Gravitational interactions would constantly disturb everything. But because space is so vast, so empty, most things can exist in relative peace. Stars can burn for billions of years without interruption. Planets can orbit in stable paths year after year, tracing the same ellipse through the darkness. When astronomers study the space between stars, they're studying the canvas on which everything else is painted. The darkness is not just absence, it's presence. It's the stage that allows everything else to happen. Without that emptiness, without those vast distances, the universe would be completely different. There would be no room for galaxies to form, no space for light to travel, no time for life to develop on quiet planets orbiting distant suns. Sometimes people find the emptiness of space frightening. All that darkness, all that distance. But there's another way to see it. The emptiness is restful. It's the universe's way of giving everything room to breathe, room to exist without pressure or crowding. In a way, the darkness between stars is like the silence between musical notes. It's what gives the bright moments their meaning. As you drift toward sleep tonight, you might imagine yourself floating in that quiet darkness, not falling, because there's no up or down in space, just floating, suspended in gentle emptiness. There's no sound except perhaps your own breathing, no light except the distant, patient glow of faraway stars, and in that darkness, you're safe, held by nothing but the vast, ancient calm of the cosmos itself. The universe has been dark for most of its history. For billions of years before the first stars formed, there was only darkness and the faint glow of the cosmic background radiation. And even now, with billions of galaxies scattered through space, most of the universe remains dark. The stars are islands of light in an ocean of peaceful shadow. And that shadow is not something to fear. It's something to rest in, so let that darkness cradle you. Let the vast emptiness of space remind you that there's room in the universe for rest, for quiet, for letting go. The stars will keep shining. The galaxies will keep turning, and you can simply drift like a particle of hydrogen floating through the cosmic night, at peace in the gentle darkness between the stars. Stars are the universe's storytellers. Every point of light you see in the night sky is a star, and each one has been shining for an incomprehensibly long time. Some stars are young, merely millions of years old. Others are ancient, nearly as old as the universe itself, burning with light that began its journey before the earth even existed. When we look at stars, we're looking backward through time, seeing the universe not as it is now, but as it was. Light travels fast. Nothing in the universe moves faster. At about 300,000 kilometers per second, light crosses vast distances. Yet even at that incredible speed, the universe is so large that light takes time to travel from one place to another. Light from the sun takes about 8 minutes to reach Earth. That means when you see the sun, you're seeing it as it was 8 minutes ago. If the sun somehow vanished right now, we wouldn't know for 8 minutes. But the sun is close, our nearest neighbor among the stars. Proxima Centauri is about 4 light years away. That means the light you see from Proxima Centauri left that star 4 years ago. It's been traveling through empty space all that time, crossing the darkness until it finally arrives here. When you see Proxima Centauri, you're seeing ancient light. You're seeing the star as it was 4 years in the past. Many stars are much farther away. Some of the stars you can see with your naked eye are hundreds of light years distant. The light from those stars began its journey hundreds of years ago. It left the star during the Middle Ages, or perhaps during the Renaissance, and has been traveling ever since. When you look at those stars, you're seeing light that's older than your country, older than modern civilization. There's something deeply calming about ancient light. It reminds us that the universe operates on timescales far longer than human concerns. While we rush through our days, light from distant stars travels peacefully through the void, patient and unchanging. It doesn't hurry. It simply moves, crossing the darkness at its own steady pace, indifferent to everything except its journey. Some stars are so far away that their light has been traveling for thousands of years. There are stars in our own galaxy, the Milky Way, whose light left them before the pyramids were built, before written language, before agriculture. That light has been traveling through space longer than human civilization has existed, and it's still traveling, still moving toward us through the cosmic night. When astronomers look at distant galaxies, they're seeing even older light. Light from galaxies millions or billions of light years away. That light began its journey when the universe was young, when the earth didn't exist, when the sun was not yet born. By the time that light reaches our telescopes, it's impossibly ancient. It's carried information across billions of years of cosmic history, preserving a moment in time from the early universe. This ancient light tells us stories. By studying the light from distant stars and galaxies, scientists can learn what those objects are made of, how hot they are, how fast they're moving. Light carries information encoded in its color, its brightness, its spectrum. Each photon of light is like a tiny messenger, carrying news from across the universe. And because light takes so long to travel, the news is always old news. We're reading messages from the past. Stars shine because of nuclear fusion. Deep in their cores, under immense pressure and heat, hydrogen atoms are crushed together to form helium. This process releases energy, which gradually works its way from the core to the surface, and then radiates out into space as light. That journey from core to surface can take thousands of years, even inside a star. Light doesn't travel in a straight line. It bounces off atoms, gets absorbed and re-emitted, zigzagging through the dense stellar material. By the time light finally reaches the surface of a star and escapes into space, it's already ancient, and then it begins the long journey through space toward Earth, toward other stars, toward distant galaxies. Some of that light will travel for billions of years without ever encountering anything. It will cross the universe, moving through the darkness, until perhaps one day it reaches a planet with someone looking up at the stars. The light from stars is remarkably constant. Stars don't flicker or change much over human timescales. They shine with steady, reliable light, day after day, year after year, century after century. This constancy is part of what makes stars comforting. They're anchors in the night sky, predictable, unchanging. You can look up and see the same patterns your ancestors saw, the same stars shining with the same light. Of course, stars do change. Over millions and billions of years, they age. They exhaust their fuel. They swell or shrink. They change color. Eventually, they die. But these changes happen so slowly that from a human perspective, stars seem eternal. The light you see tonight is essentially the same light your great-great-grandparents saw. The same light that shone on ancient civilizations, on dinosaurs, on the first life forms that crawled out of the ocean. When a star dies, its light continues to travel. Even after the star itself has collapsed or exploded, the light it emitted before its death keeps moving outward, carrying the star's last message into the universe. We sometimes see stars that no longer exist. The light from their final moments is still traveling toward us across the vast distances of space. We're seeing ghosts, echoes of stars that died long ago. There's poetry in that, the idea that light outlives its source, that a star can shine on even after it's gone, its light carrying on through the universe. It's a kind of immortality, not the star itself, but its influence, its presence, continuing long after the star has faded, in a way we're all bathed in the light of dead stars. The universe is full of these ancient photons, still traveling, still illuminating the darkness. As you lie here tonight, drifting toward sleep, you might think of yourself as surrounded by ancient light, light that's older than anything you've ever touched, older than any building or mountain or ocean. Light that began its journey in the heart of a star, billions of miles away, and traveled all that distance just to reach this moment, just to touch your eyes or your skin. You're connected to those distant stars through their light. The universe is full of light, traveling in all directions, crossing paths, interfering, reflecting, refracting. And all of it is ancient. All of it has traveled some distance, taken some time. There is no such thing as instant light, except perhaps the light created right in front of you. Everything else is a message from the past, a photon carrying news of how things were, not how they are. So rest in the knowledge that the universe is patient. That light will travel for as long as it needs to, crossing whatever distance it must. There's no rush, no deadline, just the steady, eternal movement of photons through the cosmic dark. And as you drift into sleep, you're doing something similar, moving slowly, gently, from wakefulness into dreams, from consciousness into rest. Like light crossing the universe, you're on a journey, and there's no need to hurry. Let the ancient light of stars be a lullaby. Let it remind you that some things are timeless, that some journeys are worth taking slowly. The stars have been shining for billions of years. They'll keep shining tonight, and their light will reach you, even in your dreams, connecting you to the vast, peaceful cosmos that surrounds us all. Galaxies are islands of stars, massive collections of billions, or even hundreds of billions of suns, all held together by gravity. Our own galaxy, the Milky Way, is one of billions of galaxies in the observable universe. Each galaxy is like a separate world, a community of stars that have been traveling together through space for billions of years. And all of them are moving, drifting through the universe in a slow cosmic dance. When you look at a galaxy, even through a powerful telescope, it seems still, frozen in place like a photograph. But that stillness is an illusion created by distance and time. Galaxies are moving, they're rotating, spinning like enormous pinwheels in the darkness. They're also moving through space itself, drifting away from some galaxies and toward others, pulled by gravity and carried by the expansion of the universe. The Milky Way is a spiral galaxy. It has long, curved arms that extend from a central bulge, creating a shape that's beautiful and graceful. These spiral arms are not solid structures. They're more like waves, regions where stars are slightly more concentrated than elsewhere. As the galaxy rotates, these waves move through the stars, creating the impression of spirals. The stars themselves move in and out of the spiral arms, taking millions of years to complete their orbits around the galactic center. Our sun is located about halfway out from the center of the Milky Way. In one of those spiral arms, we're traveling around the galactic center at about 220 kilometers per second. That sounds fast, and it is. But the galaxy is so large that it takes the sun about 225 million years to complete one orbit. The last time the sun was in this position in the galaxy, dinosaurs were just beginning to appear on Earth. The galaxy's rotation is so slow that we'll never see any change in our lifetimes. Other galaxies have different shapes. Some are elliptical, looking like glowing eggs or spheres. These galaxies have less structure than spiral galaxies. Their stars orbit the center in random directions, creating a smooth, diffuse glow. Elliptical galaxies are often older, formed from the collision and merger of smaller galaxies. When galaxies collide, they don't crash like solid objects. They pass through each other, their stars rarely touching, because the distances between stars are so vast, but gravity pulls them together, and over time, they merge into a single, larger galaxy. There are also irregular galaxies, galaxies without any clear shape. These are often younger, still forming stars, still being shaped by gravity and galactic winds. They're chaotic, beautiful in their disorder. And there are dwarf galaxies, small galaxies with only a few billion stars. These tiny galaxies often orbit larger ones, like moons orbiting a planet. The Milky Way has several dwarf galaxies orbiting it, small companions that travel with us through the universe. All galaxies are moving away from each other on average. This is because the universe itself is expanding. Space is stretching, and as it stretches, it carries galaxies with it. The farther away a galaxy is, the faster it appears to be moving away from us. This discovery, made in the 1920s by Edwin Hubble, changed our understanding of the universe. It showed us that the universe had a beginning, that it started small and has been growing ever since. This expansion is gentle. It's not like an explosion with galaxies flying through space. Instead, space itself is growing, creating more distance between galaxies over time. Imagine dots on the surface of a balloon. As you inflate the balloon, the dots move apart, not because they're traveling across the surface, but because the surface itself is expanding. That's what's happening to the universe on a cosmic scale. But not all galaxies are moving apart. Some are moving toward each other, drawn together by gravity. The Milky Way, for example, is on a collision course with our nearest large neighbor, the Andromeda Galaxy. In about 4 billion years, these two galaxies will collide. It will be a slow collision, taking millions of years, and it will create a new, larger galaxy. By that time, the sun will be nearing the end of its life, and Earth will be very different, if it still exists at all. Galaxies often exist in groups or clusters. Our Milky Way is part of something called the local group, a collection of about 50 galaxies bound together by gravity. The local group is itself part of a larger structure, a supercluster called Laniakea, which contains about 100,000 galaxies. These structures are the largest in the universe. Vast webs of galaxies stretching across hundreds of millions of light years. Between these structures are voids, vast regions of space that contain very few galaxies. These voids are not truly empty, but they're close. They're like the bubbles in foam, with galaxies concentrated along the edges. The universe has a structure, a cosmic web of filaments and voids, created by gravity over billions of years. It's a pattern so large that we can barely comprehend it. Yet, it's as real as the pattern of cities and roads on Earth. As galaxies drift through space, they interact with each other in subtle ways. Their gravity affects nearby galaxies, pulling them slightly off course, disturbing their rotation, triggering waves of star formation. Sometimes a small galaxy passes too close to a large one and is torn apart, its stars scattered into long streams that orbit the larger galaxy. These tidal streams are like ghostly ribbons, the remains of galaxies that once existed but were consumed by their larger neighbors. The Milky Way has consumed many smaller galaxies over its history. We can see the evidence in streams of stars that orbit our galaxy in unusual patterns, remnants of dwarf galaxies that wandered too close. This process is still happening. Right now, there are small galaxies being slowly pulled apart by the Milky Way's gravity. Their stars joining our galaxy's vast collection. It's a gentle kind of growth, adding a few billion stars here and there over millions of years. Inside galaxies, stars drift in their orbits, each one following its own path. They don't collide because they're so far apart. Even in the dense center of the galaxy, where stars are packed more closely together, the distances are still vast. A star might go its entire lifetime without ever coming close to another star. It's a lonely existence, in a way, but also a peaceful one. Each star has room to shine, room to exist without interference. Galaxies also contain vast amounts of dark matter, a mysterious substance that doesn't emit light but exerts gravitational pull. In fact, most of the mass in a galaxy is dark matter, not stars. This dark matter forms a halo around the galaxy, extending far beyond the visible stars. We can't see it directly, but we can see its effects. It holds the galaxy together, keeping it from flying apart as it rotates. Without dark matter, galaxies like the Milky Way wouldn't exist. There's something calming about imagining galaxies drifting through the universe, these enormous structures, each containing billions of stars, floating through space like dandelion seeds on a breeze. They move so slowly that they seem still, yet they're in constant motion, following paths determined by gravity and the expansion of space. They've been moving like this for billions of years, and they'll continue for billions more. As you rest here tonight, you might picture the Milky Way as seen from outside, a spiral of stars glowing softly in the darkness. Picture our sun as one tiny point of light among billions, orbiting slowly around the galactic center. And picture yourself on a planet orbiting that sun, a small world spinning through space, part of this vast, peaceful drift of galaxies through the cosmic night. You're part of that drift. We all are. We're passengers on a planet that orbits a star, that orbits a galaxy, that drifts through space. And all of that motion is smooth, gentle, unstoppable. There's no friction in space, no resistance, just the steady pull of gravity and the slow expansion of the universe. It's like floating on a calm sea, rocking gently with the waves, moving without effort. Let that image carry you toward sleep. The galaxies drifting, the stars orbiting, the universe expanding, all of it happening at a pace so slow, so gentle, that it feels like stillness. And in that stillness, you can rest. You can let go of your thoughts, let go of your worries, and simply drift like a galaxy through the cosmic dark, peaceful and unhurried, surrounded by the quiet beauty of the universe. Nebulae are among the most beautiful objects in the universe. These clouds of gas and dust glow with soft colors, illuminated by nearby stars or shining with their own light. Some nebulae are vast, spanning dozens of light years. Others are smaller, more compact. But all of them are places of creation, Nebulae are stellar nurseries, the places where new stars are born, where the universe renews itself through a process that has continued for billions of years. The most famous nebula is probably the Orion Nebula, visible to the naked eye as a fuzzy patch in the constellation Orion. Through a telescope, it reveals itself as a glowing cloud of gas, pink and red and blue, with bright young stars embedded within it. Those stars were born recently in cosmic terms, just a few million years ago. They're still in their infancy, surrounded by the remnants of the cloud that created them. Stars form when clouds of gas and dust collapse under their own gravity. These clouds, called molecular clouds, are cold and dark, made mostly of hydrogen with traces of other elements. They can be enormous, containing enough material to create thousands of stars. But they're also incredibly diffuse, thinner than the best vacuum on Earth. For a long time, these clouds drift through space, undisturbed, just cold gas floating in the darkness between stars. Sometimes, something disturbs the cloud. Perhaps a nearby star explodes, sending a shock wave through space. Perhaps two clouds collide. Perhaps the cloud simply becomes dense enough that gravity begins to pull parts of it together. Whatever the trigger, once a region of the cloud starts to collapse, the process accelerates. As the gas falls inward, it heats up. Gravity pulls more material in, and the center of the collapsing region becomes denser and hotter. This collapse takes time, thousands or millions of years. The cloud fragments into smaller pieces, each piece collapsing independently, each one potentially forming a star. The centers of these collapsing regions grow hotter and denser until eventually the temperature and pressure become high enough for nuclear fusion to begin. Hydrogen atoms start fusing into helium, releasing energy. At that moment, a star is born. The cloud stops collapsing, balanced now by the outward pressure of the energy produced by fusion. The newborn star is still surrounded by gas and dust, the leftover material from the cloud. This material forms a disk around the star, a spinning pancake of gas gradually dissipates over millions of years. In some of these disks, planets form. The dust particles stick together, forming larger and larger clumps, which eventually become asteroids, then planets. Our own solar system formed this way about 4.5 billion years ago from a collapsing cloud of gas and dust. Young stars are often bright and hot. They emit intense radiation that lights up the surrounding gas, making the nebula glow. This is what creates the beautiful colors we see in images of nebulae. The gas absorbs the starlight and re-emits it at specific wavelengths, creating the reds of hydrogen, the greens of oxygen, the blues of other elements. Each color tells us something about the gas, about its temperature and composition. Not all nebulae are stellar nurseries. Some are the remnants of dead stars. When a massive star reaches the end of its life, it can explode in a supernova, ejecting its outer layers into space. These ejected layers form an expanding shell of gas, glowing from the energy of the explosion. Over thousands of years, the shell expands and fades, eventually mixing with the interstellar medium. These are called supernova remnants, and they're spectacular, with intricate filaments and shells of glowing gas. Another type of nebula forms when a star like our sun dies. Stars like the sun don't explode. Instead, they gently shed their outer layers as they age, creating a shell of gas that expands away from the dying star. The hot core of the star, now exposed, emits ultraviolet light that causes the shell to glow. These are called planetary nebulae, though they have nothing to do with planets. The name comes from early astronomers who thought they looked like planets through small telescopes. Planetary nebulae are often symmetrical and beautiful, with rings, shells, or hourglass shapes. They come in many forms, each one unique, shaped by the rotation of the dying star, by magnetic fields, by companion stars. They last for only a few tens of thousands of years before fading away, dispersing into space. But during their brief existence, they're some of the most striking objects in the sky. All nebulae, whether they're stellar nurseries or remnants of dead stars, are part of the cosmic cycle. Stars are born from gas clouds. They live for millions or billions of years, fusing hydrogen into heavier elements. When they die, they return that material to space, enriching the interstellar medium with elements like carbon, oxygen, and iron. These elements become part of new gas clouds, which collapse to form new stars, and so the cycle continues. This means that the atoms in your body, the carbon in your cells, the oxygen you breathe, were forged inside stars that lived and died billions of years ago. Those stars exploded or shed their outer layers, creating nebulae that eventually collapsed to form the sun and planets. We are, quite literally, made of star stuff. We're part of the cosmic cycle, connected to the universe in the most fundamental way. There's something deeply peaceful about nebulae. They glow softly in the darkness, like lanterns in the night. They're places of creation, where the universe makes new stars, new worlds, new possibilities. And they're places of rest, where old stars return their material to space, completing the cycle. They remind us that nothing is permanent, that everything changes, but also that nothing is truly lost. The material just transforms, taking new shapes, new forms. When you imagine a nebula, picture a vast cloud of gas, glowing with soft pink and blue light. Picture stars forming within it, pinpricks of brightness scattered through the cloud. Picture the gas slowly swirling, shaped by gravity and starlight and magnetic fields. It's a slow process, so slow that you could watch for a human lifetime and see no change. But it's happening. New stars are being born. Old stars are dying. The universe is renewing itself. As you drift toward sleep, you might think of yourself as part of this cosmic process. You're made of atoms that were once inside stars, that were once part of nebulae drifting through space. Those atoms have taken many forms over billions of years. They've been part of stars, part of planets, part of living things. And now they're part of you, arranged in the particular pattern that makes you who you are. One day, those atoms will return to the universe. be part of the Earth, then perhaps the Sun, then perhaps a nebula far in the future. They'll become part of new stars, new planets, maybe even new life. The cycle will continue as it always has, driven by gravity and time and the endless creativity of the cosmos. And in that cycle, there's a kind of immortality, not for us as individuals, but for the atoms that make us up. So rest easy tonight, knowing that you're part of something vast and ancient and beautiful. You're part of the universe's story, a story that began nearly 14 billion years ago and will continue for trillions of years to come. You're connected to nebulae, to stars, to galaxies, to everything that exists. And in that connection, there's comfort. You're not separate from the universe. You're part of it, made of the same stuff, following the same laws, part of the same great cycle of creation and renewal. Let the soft glow of nebulae be your night light as you drift into dreams. Let the slow birth of stars remind you that some things take time. That patience is built into the fabric of the cosmos, and let yourself rest in the knowledge that you're part of something beautiful, something ancient, something that will endure long after your dreams have faded into morning. Gravity is the force that holds the universe together. It's what keeps your feet on the ground, what keeps the moon orbiting Earth, what keeps Earth orbiting the sun. It's what binds stars into galaxies and galaxies into clusters. Without gravity, the universe would be a very different place. There would be no stars, no planets, no structure at all. Just atoms drifting randomly through space, never coming together to form anything. Gravity is also the gentlest of the fundamental forces. It's much weaker than the electromagnetic force, much weaker than the nuclear forces that hold atoms together. You can overcome gravity easily. Just lift your hand, just jump, but gravity never stops. It never turns off. It's always there, always pulling, patient and persistent. And given enough time, gravity always wins. The way gravity works is beautifully simple. Every object with mass attracts every other object with mass. The The more massive an object is, the stronger its gravitational pull. The farther apart two objects are, the weaker the pull between them. That's it. That's the entire law, at least in its simplest form. Yet, from this simple rule, all the complexity of the cosmos emerges. When you stand on Earth, you're being pulled down by the planet's gravity, but you're also pulling the Earth up toward you with your own gravity. It's just that Earth is so much more massive than you are that your pull on Earth is imperceptible. Still, it exists. Every atom in your body is pulling on every atom in the planet. Gravity connects you to the Earth, and through the Earth to everything else in the universe. The moon orbits Earth because of gravity. Earth's gravity pulls on the moon, and the moon's gravity pulls on Earth. The moon is trying to move in a straight line, as all objects naturally do. But Earth's gravity constantly pulls it off that straight path, bending it into a curve. The result is an orbit, a balance between the moon's motion and Earth's pull. The moon has been orbiting Earth for over 4 billion years, pulled by gravity, never straying from its path. Earth orbits the sun for the same reason. The sun's gravity reaches out across 150 million kilometers of space, pulling Earth into its orbit. All the planets orbit the sun this way, each one held in place by gravity, each one following an elliptical path that it's been following for billions of years. The solar system is a gravitational dance, with the sun as the center and the planets as dancers, circling endlessly to the rhythm of gravity's pull. Gravity also holds stars together. A star is a ball of hot gas, and that gas would naturally want to expand, spreading out into space. But gravity pulls it inward, compressing it. The star exists in a balance between the outward pressure of heat and the inward pull of gravity for most of a star's life. That balance is stable. The star burns steadily, neither expanding nor contracting. Only when the star runs out of fuel does the balance break, and gravity finally wins. When a massive star dies, gravity causes it to collapse. The outer layers fall inward, compressed to incredible densities. In some cases, the collapse is so complete that nothing can stop it. The core shrinks to a point, creating a black hole, a region of space where gravity is so strong that not even light can escape. Black holes are gravity at its most extreme, places where the gentle pull becomes an irresistible grip. But even black holes are just following the same simple rules as everything else. They're massive objects, so they have strong gravity. Objects that get too close are pulled in. That's all. They're not cosmic vacuums, sucking up everything around them. They don't reach out and grab things. They just sit there, pulling on nearby objects with gravity, just like any other massive object. It's just that their gravity is so strong and their size so small that strange things happen near them. Gravity also shapes the large-scale structure of the universe. In the early universe, matter was distributed almost evenly, but there were tiny variations, regions where the density was slightly higher. Gravity amplified those variations. The denser regions pulled in more matter, becoming denser still over billions of years. This process created the cosmic web, the filaments and clusters of galaxies we see today. All from gravity, patiently pulling matter together over eons. One of the most beautiful things about gravity is that it acts at a distance. You don't have to touch something to feel its gravity. Earth's gravity reaches out through space to hold the moon in orbit. The sun's gravity reaches out to hold the planets. The Milky Way's gravity reaches out to hold hundreds of billions of stars in their orbits. Gravity connects everything, linking objects across vast distances, creating a web of invisible influence that spans the entire universe. Einstein taught us that gravity isn't really a force in the way we usually think of forces. It's actually a curvature of space and time. Massive objects like stars and planets create a dip in the fabric of space, like a bowling ball on a trampoline. Other objects roll into that dip, and we perceive that as gravity. Light follows the curves of space too, which is why light bends around massive objects. Gravity isn't pulling light, Space itself is curved, and light is just following the straightest path it can through curved space. This might sound complicated, but it's actually quite elegant. Space and time are flexible. They bend and curve in the presence of mass. Objects follow the curves, moving along paths determined by the shape of space. That's gravity. It's geometry. The universe is a curved, flexible landscape, and everything in it is just following the natural contours of that landscape. There's something soothing about gravity's constancy. It's always there, always the same. It doesn't change with temperature or pressure. It doesn't depend on what something is made of, only on how much mass it has. Gravity treated the first atoms in the universe exactly the same way it treats atoms today. It's been operating by the same rules for nearly 14 billion years, and it will continue to operate by those rules for trillions of years to come. Gravity is also patient. It works slowly, steadily, over long periods of time. It took millions of years for gravity to pull gas clouds together to form the first stars. It took billions of years for gravity to create galaxies. It will take trillions of years for gravity to pull the last stars together into black holes. In the far future, when the universe is old and dark, gravity is in no hurry. It has all the time in the universe. When you lie down to sleep, you feel gravity pulling you down into your bed. It's a gentle, constant pressure holding you in place. That same force is holding the moon in orbit, holding Earth around the sun, holding the solar system together. You're connected to all of that through gravity. You're part of the gravitational web that binds the universe together. As you relax into sleep, you might imagine gravity as a soft blanket, gently pressing down, holding you safe and secure. It's been holding you your entire life, every moment of every day. It's so constant that you don't even notice it most of the time. But it's there, always, a gentle, persistent reminder that you're part of something larger, something cosmic. Let gravity ease you into rest. Let its gentle, constant pull be a comfort. The same force that holds planets in orbit, that shapes galaxies, determines the structure of the universe, is holding you right now. You're safe in gravity's embrace, just as you've always been. And as you drift into sleep, you're not falling. You're being held gently, constantly, by the oldest, most fundamental force in the universe. Gravity doesn't demand anything from you. It doesn't ask you to stay awake or pay attention. It just holds you, supports you, keeps you grounded. And tonight, that's all you need. To be held, to be supported, to rest in the gentle, eternal pull of gravity, knowing that it will be there tomorrow and the day after and forever. So let go. Let gravity do its work and drift into the deep, peaceful sleep that comes from knowing you're held by the universe itself. For most of human history, we knew of only one planetary system, our own. The Sun, surrounded by 8 planets, along with moons and asteroids and comets. We wondered if other stars had planets too, but we had no way to know. The distances were too great, the planets too small and dim. But in the 1990s, astronomers began finding planets orbiting other stars. These exoplanets, as they're called, have changed our understanding of the universe. We now know that planets are common. Most stars have them. The first exoplanets discovered were giants, worlds much larger than Earth, orbiting close to their stars. They were easier to detect because of their size and proximity to their suns. Some orbit their stars in just a few days, whipping around in tight circles. These hot Jupiters, as they're called, are very different from anything in our solar system. They're gas giants like Jupiter, but they orbit so close to their stars that their atmospheres are heated to thousands of degrees. They glow with their own heat, scorched by starlight. But as detection methods improved, astronomers began finding smaller planets, planets more like Earth, rocky worlds orbiting in the habitable zone, the region around a star where temperatures are just right for liquid water to exist. Water is essential for life as we know it, so these planets are of particular interest. They might have oceans, atmospheres, maybe even life. We don't know yet, but the possibility is there and it's exciting. Some exoplanets are truly exotic. There are lava worlds, planets so close to their stars that their surfaces are molten rock. There are ice giants, worlds covered in deep oceans with thick atmospheres of hydrogen and helium. There are rogue planets, worlds that don't orbit any star at all, drifting alone through the darkness of space. There are planets orbiting binary stars with two suns in their sky instead of one. The variety is astounding. Many exoplanets orbit red dwarf stars, small, cool stars that are the most common type in the galaxy. Red dwarfs are dim, so their habitable zones are close in. Planets in the habitable zone of a red dwarf orbit their star in just a few weeks. They're likely tidally locked, meaning one side always faces the star while the other side is in perpetual night. These worlds would be strange, with one hemisphere in eternal day and the other in eternal night, and a narrow band around the equator where conditions might be just right for life. We've discovered thousands of exoplanets so far, and there are likely billions more in our galaxy alone. Every star you see in the night sky probably has planets. Some have multiple planets, entire systems like our own. Some planets are alone. Some are in pairs or groups. Some orbit close, some far. Some are hot, some cold. The universe is full of worlds, each one unique, each one following its own path around its own star. The methods we use to find exoplanets are ingenious. Most are found using the transit method. When a planet passes in front of its star, it blocks a tiny amount of the star's light. By carefully monitoring the brightness of stars, astronomers can detect these tiny dips and infer the presence of a planet. They can even learn about the planet's size, orbit, and sometimes its atmosphere by analyzing the light that passes through the planet's atmosphere during the transit. Another method is the radial velocity method. A planet doesn't just orbit its star. The star also orbits the planet, or more precisely, both orbit their common center of mass. This causes the star to wobble slightly. By measuring the star's motion, astronomers can detect the presence of planets and learn about their mass and orbit. It's a subtle effect, but with precise instruments, it's detectable. Some exoplanets have been directly imaged. This is incredibly difficult because planets are so much dimmer than their stars. It's like trying to see a firefly next to a spotlight. But by using special instruments that block the star's light, astronomers have managed to take pictures of a few exoplanets. These images show the planets as tiny dots of light, faint and distant, but real. Each exoplanet is a world with its own story. Some are young, still hot from their formation. Some are old, cool, their surfaces ancient and cratered. Some have atmospheres, thick blankets of gas that trap heat or reflect light. Some are bare rock, exposed to the harsh radiation of their stars. Some have moons, some have rings. Each one is different, shaped by its formation, its orbit, its star. We wonder if any of these planets harbor life. It's one of the great questions of our time. Are we alone in the universe, or is life common? We don't know yet. We haven't found definitive evidence of life beyond Earth. But we're looking. We're studying exoplanet atmospheres, searching for signs of oxygen, methane, other gases that might be produced by living organisms. We're listening for radio signals, signs of intelligent civilizations. So far, we've found nothing. But the search continues. Even if we don't find life, the existence of exoplanets is profound. It tells us that the processes that formed our solar system are common. That planets form naturally around stars. That the universe is full of worlds, places where, in principle, life could exist. It expands our perspective, makes us realize how vast the universe is, how many possibilities it contains. Some of these planets might have oceans, deep, dark waters covering their entire surface, kilometers deep. Life on Earth began in the ocean. So perhaps life on other worlds did too. We imagine creatures swimming in those alien seas, adapted to the light of a different sun, living lives utterly different from ours, but still recognizable as life. It's a beautiful thought, even if it's just speculation for now. Other planets might have continents, mountains, rivers, weather. They might have seasons as they orbit their stars. They might have ice caps at their poles, deserts at their equators. They might have volcanoes, earthquakes, plate tectonics. All the geological processes that shape Earth might be happening on countless other worlds, creating landscapes we've never seen, environments we can barely imagine. As you rest here tonight, drifting toward sleep, you might picture one of these distant planets. Imagine a rocky world orbiting a dim red star. The star hangs low on the horizon, large and red, bathing the landscape in crimson light. The sky is a deep purple, dotted with unfamiliar stars. The air is thin, cool. There are mountains in the distance, their peaks catching the red light. And it's quiet, profoundly quiet. No birds, no insects, no wind, just stillness. Or imagine a moon orbiting a giant planet, like Saturn but larger. The giant planet fills half the sky, its rings stretching across the horizon, glowing softly in the light of the distant sun. The moon's surface is ice, smooth and white, with cracks and ridges where the ice has shifted. Beneath the ice is an ocean, dark and deep, kept liquid by the tidal heating from the giant planet's gravity. In that ocean, perhaps, something lives, something we've never imagined. These worlds exist right now, scattered across the galaxy. Billions of planets are orbiting their stars. Some are bathed in light, some in darkness, some are warm, some frozen. Some are young, some old. Each one is a place, a real location in space, with its own environment, its own characteristics. And each one is following its orbit, a path determined by gravity and momentum, moving through space with the patience of the cosmos. You're orbiting too, of course. You're on Earth, and Earth is orbiting the sun. Right now, even as you lie still, you're moving through space at about 30 kilometers per second. You're following Earth's orbit, a path that takes 1 year to complete, a path that Earth has followed billions of times. And the sun is moving too, orbiting the center of the galaxy. the galaxy itself is moving through space. Everything is in motion. Everything is orbiting something, following the gentle pull of gravity through the cosmic dark. Let that motion lull you to sleep. You're a passenger on a planet, orbiting a star, in a galaxy, in a universe, and all of that motion is smooth, gentle, eternal. There's no friction, no resistance, just the endless dance of gravity and momentum. Planets orbiting stars, moons orbiting planets, everything moving in harmony. You're part of that dance. And as you drift into sleep, you're still dancing, still moving through space, part of the great cosmic ballet that has been going on for billions of years and will continue for billions more. Rest easy, knowing that countless worlds are out there, orbiting their stars in the darkness. Some are warm, some cold. Some might have life, most probably don't. But all of them are part of the universe, just like you. All of them are following the same laws, moving to the same rhythms. And in that shared existence, there's a kind of kinship. You're not alone in the universe. You're part of it, connected to every planet, every star, every galaxy, by the simple fact that we all exist in the same cosmos, following the same rules, moving through the same space and time. The universe has a temperature. Right now, at this moment, space itself has a temperature of about 2.7 degrees above absolute zero. That's about minus 270 degrees Celsius. It's incredibly cold, far colder than anything we experience on Earth. But it's not quite absolute zero. Space has some heat in it, left over from the very beginning of the universe. This faint warmth is called the cosmic microwave background, and it's one of the most important discoveries in astronomy. The cosmic microwave background, or CMB, is light that has been traveling through space for almost 14 billion years. It was released when the universe was very young, just 380,000 years after the Big Bang. Before that, the universe was too hot and dense for light to travel freely. It was a glowing fog of particles and radiation, opaque to light. But But as the universe expanded and cooled, it became transparent. Light could finally travel freely. That first light is what we see today as the CMB. When the CMB was first released, it was bright and hot. But as the universe expanded, the light was stretched. The wavelengths became longer, shifting from visible light to infrared, then to microwaves. That's why we call it the cosmic microwave background. It's not visible to our eyes. It's microwave radiation, the same type used in microwave ovens, but much, much fainter. To detect it, you need sensitive instruments, radio telescopes tuned to the right wavelengths. The CMB fills the entire sky. No matter which direction you look, it's there. A faint glow of microwave radiation coming from every point in space. It's the oldest light in the universe, a snapshot of what the cosmos looked like when it was just beginning. By studying the CMB, astronomers can learn about the early universe, about its temperature, its density, its composition. It's like looking at a baby picture of the universe. The CMB is remarkably uniform. Its temperature is almost exactly the same in all directions, varying by only tiny fractions of a degree. This tells us that the early universe was very smooth, very homogeneous. Matter and energy were distributed almost evenly throughout space. But there are small variations, tiny differences in temperature from one region to another. These variations are incredibly important because they're the seeds of all the structure we see today. The slightly hotter regions in the CMB correspond to areas where the early universe was slightly denser. Gravity amplified these density differences over time, pulling matter together to form stars, galaxies, and clusters. The cold spots correspond to regions that were slightly less dense and became the voids we see today. The pattern of hot and cold spots in the CMB is like a map of the early universe, showing where galaxies would eventually form. Studying the CMB has told us a great deal about the universe. It's confirmed that the universe is about 13.8 billion years old. It's told us what the universe is made of. About 5% ordinary matter, 27% dark matter, and 68% dark energy. It's shown us that the universe is flat, meaning its overall geometry is Euclidean, not curved. These are profound discoveries, and they all come from studying the faint glow of the CMB. The CMB is also incredibly smooth, which tells us something surprising about the early universe. Different regions of space that are now far apart were once close together, in contact with each other. This explains why the CMB has almost the same temperature everywhere. The early universe had time to even out temperature differences before it started expanding rapidly. This rapid expansion, called inflation, stretched the universe by an enormous factor in a tiny fraction of a second. Inflation is a remarkable idea. It suggests that the universe underwent a brief period of exponential expansion in the first moments after the Big Bang. This expansion smoothed out any irregularities and set the stage for the universe we see today. The CMB provides evidence for inflation by showing just how uniform the early universe was. Without inflation, different parts of the CMB would have very different temperatures because they would never have been in contact. The CMB is also polarized, meaning the light waves oscillate in particular directions. This polarization carries information about conditions in the early universe. By measuring it, astronomers can learn about the density of matter, the behavior of dark energy, and even search for signs of gravitational waves from the inflationary epoch. The polarization patterns in the CMB are like fingerprints, each one telling a story about the forces and processes that shaped the early universe. There's something deeply peaceful about the CMB. It's a reminder that the universe had a beginning, that there was a time when everything was different. And yet, the light from that beginning is still here, all around us, filling space with a faint glow. It's been traveling for nearly 14 billion years, longer than stars have existed, longer than galaxies, longer than Earth. It's the oldest thing we can see, and it's everywhere. When you think about the CMB, you're thinking about the universe at its most fundamental level. You're looking back in time, seeing the cosmos as it was just after it became transparent. You're seeing the seeds of everything that exists today. Every galaxy, every star, every planet, including Earth, formed from the tiny density variations in the CMB. In a sense, the CMB is a map of our cosmic ancestry, showing where we came from. The CMB also tells us about the future. By measuring how the universe has expanded over time, astronomers can predict what will happen in the future. The universe will continue to expand, growing larger and colder. Galaxies will drift farther apart. Stars will exhaust their fuel and die. Eventually, trillions of years from now, the universe will be a very different place, dark and cold, but the CMB will still be there, even fainter than it is now, still carrying information about the beginning. As you lie here, drifting toward sleep, you might imagine the CMB as a blanket of light, invisible to your eyes, but surrounding you on all sides. It's been traveling through space for almost the entire history of the universe. And it's here now, passing through you at this very moment. Microwaves from the beginning of time, carrying the story of the cosmos, filling every corner of space with their faint, persistent glow. There's comfort in the idea that the universe has a background, a baseline temperature, a faint warmth left over from its birth. Even in the coldest, emptiest reaches of space, there's still this glow, this reminder that the universe began hot and has been cooling ever since. It's like the embers of a fire, glowing softly long after the flames have died. The universe is cooling, but it's not cold yet. There's still warmth, still light, still energy moving through space. The CMB is also a reminder of how much we've learned. 100 years ago, we didn't know the universe had a beginning. We didn't know it was expanding. We didn't know about the CMB. Now we can measure it with incredible precision, learning about the universe's age, its composition, its history. It's a triumph of science, of human curiosity, and ingenuity, and it all comes from studying a faint glow in the sky. Light so old it's older than the stars. As you drift into sleep, let the CMB be a lullaby. Let it remind you that the universe is ancient, vast, and full of mysteries we're still unraveling. Let it remind you that you're part of a story that began nearly 14 billion years ago. A story that's still being written, still unfolding. And let it remind you that even in the darkest, coldest places, there's still light, still warmth, still the faint echo of the universe's birth. The CMB is patient, eternal, unchanging. It's been here since the beginning, and it will be here until the end. It doesn't ask for anything. It just exists, filling space with its gentle glow. And tonight, as you sleep, it's here with you, surrounding you, connecting you to the earliest moments of the universe. Rest in that connection. Rest in that ancient light. And let it carry you into dreams as deep and old as time itself. Black holes are among the most mysterious objects in the universe. They're regions of space where gravity is so strong that nothing, not even light, can escape. Once something crosses the boundary of a black hole, called the event horizon, it's gone forever, pulled inexorably toward the center. We can't see black holes directly because they don't emit light. But we can see their effects on nearby matter and light. And from those effects, we've learned that black holes are real, and they're common. Black holes form when massive stars die. When a star much larger than the sun exhausts its fuel, it can no longer support itself against gravity. The core collapses, and if the star is massive enough, the collapse doesn't stop. It continues until all the mass is compressed into an incredibly small space, perhaps even a single point. At that moment, the star becomes a black hole. The gravity near this tiny, dense core is so strong that it warps space itself, creating the event horizon. The event horizon is not a physical surface. It's just a boundary, a point of no return. If you cross it, you can't come back. Inside the event horizon, all paths lead to the center of the black hole. It's not that you're being pulled harder, it's that space itself is so curved that there's no direction that leads out. It's like being on a slope so steep that no matter which way you walk, you go downward. That's what the inside of a black hole is like, except instead of a slope, it's the fabric of space and time itself. Black holes warp time as well as space. The closer you get to a black hole, the slower time passes from the perspective of someone farther away. If you could watch someone fall into a black hole, you'd see them slow down as they approached the event horizon. They'd never quite seem to cross it. They'd appear frozen at the edge, their image growing dimmer and redder over time. But from their perspective, they'd cross the horizon in finite time and continue falling toward the center. At the very center of a black hole is the singularity, a point where density becomes infinite and the laws of physics, as we understand them, break down. We don't really know what happens at the singularity. Our theories can't describe it. It's a place where space and time lose their usual meaning. But the singularity is hidden behind the event horizon, so we can't see it or study it directly. It's the ultimate mystery, locked away inside the black hole. Not all black holes are formed from dying stars. Some are much larger, millions or even billions of times the mass of the sun. These supermassive black holes are found at the centers of galaxies, including our own Milky Way. The black hole at the center of the Milky Way is called Sagittarius A, and it has a mass of about 4 million suns. Despite its enormous mass, it's remarkably quiet, only occasionally consuming gas or stars that wander too close. Supermassive black holes grow by consuming matter, gas, dust, and even entire stars can fall into them, adding to their mass. As matter spirals into a black hole, it forms an accretion disk, a swirling disk of material that heats up due to friction. This disk can become incredibly hot, emitting intense radiation. Some of the brightest objects in the universe, called quasars, are powered by supermassive black holes, consuming vast amounts of matter. They can outshine entire galaxies. Black two black holes orbit each other, they gradually lose energy to gravitational waves, ripples in the fabric of space and time. Over time, the orbit shrinks, and eventually, the black holes collide and merge into a single, larger black hole. This collision releases an enormous amount of energy in the form of gravitational waves, which can be detected by instruments on Earth. We've now observed many such mergers, confirming that black holes can pair up and combine. Gravitational waves are one of the most exciting discoveries in recent astronomy. They were predicted by Einstein over a century ago, but they're so faint that it took decades to develop instruments sensitive enough to detect them. When gravitational waves pass through Earth, they stretch and compress space itself by a tiny amount. By measuring these tiny changes, scientists can detect the waves and learn about the events that produced them. Like black hole mergers or colliding neutron stars, there's something fascinating about black holes' effect on space and time. Near a black hole, space is so warped that light can orbit the black hole multiple times before escaping or falling in. If you were near a black hole, you could theoretically see the back of your own head, because light from behind you would curve around the black hole and reach your eyes. It's a strange, almost surreal environment where the usual rules don't apply. Black holes also have a connection to the ultimate fate of matter. Anything that falls into a black hole is lost to the outside universe, at least in classical physics. But quantum mechanics suggests that black holes aren't completely black. They emit a faint radiation called Hawking radiation, named after physicist Stephen Hawking. This radiation is incredibly faint, especially for large black holes, but it's real. Over unimaginably long periods of time, black holes can evaporate, slowly losing mass until they finally disappear. This means that black holes aren't eternal. Given enough time, even the largest black hole will evaporate. But the timescales involved are enormous. A black hole with the mass of the sun would take about 10 to the 67 years to evaporate. That's a trillion, 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 trillion years. are permanent. But in the ultimate end, they too will fade away, returning their energy to the universe. Despite their fearsome reputation, black holes are not cosmic vacuum cleaners. They don't reach out and suck things in. They're just massive objects with strong gravity. If the sun were replaced by a black hole of the same mass, Earth would continue to orbit exactly as it does now. The black hole's gravity would be the same as the sun's gravity at our distance. You'd only notice a difference if you got very close to the black hole, close enough that the warping of space became significant. In fact, most black holes are quite isolated. They sit quietly in space, not interacting with much. Only when something passes very close do they have any effect. The rest of the time, they're just massive objects warping space around them, invisible unless you know where to look. They're part of the cosmic landscape, as natural and unremarkable in a way as stars or planets. As you rest here tonight, you might imagine space as a fabric, like a stretched sheet. Massive objects create dips in this fabric, and other objects roll into those dips, following the curves. A black hole creates the deepest dip of all, a well so steep that nothing can climb back out. But from a distance, the fabric is smooth. The dip is there, but it's just part of the landscape. Space is flexible, accommodating, shaped by mass and energy. There's a beauty to this idea that space itself can bend and curve. It makes the universe feel more alive, more dynamic. Space isn't just a backdrop. It's an active participant in the cosmos. It responds to matter and energy, curving and warping, creating the gravitational effects we observe. And understanding this helps us see the universe more clearly, as a place where everything is connected, where matter and space and time are all part of one unified whole. Black holes remind us that the universe has extremes, places where the rules are pushed to their limits, where gravity is so strong, space so curved, that new phenomena emerge. They're laboratories for testing our understanding of physics, places where general relativity meets quantum mechanics, where the universe reveals its deep even though we can't visit a black hole, we can study them, learn from them, and marvel at their existence. As you drift into sleep, let the thought of black holes ground you. They're the universe's anchors, massive and immovable, holding galaxies together, shaping the cosmos. They're patient, eternal for all practical purposes, sitting quietly in the dark, waiting. And in their patience, there's a lesson. Some things can't be rushed. Some things simply are, existing beyond our concerns, beyond our time frames. Black holes have been around for billions of years, and they'll be around for billions more. They're part of the permanent architecture of the universe. So rest easy, knowing that the universe has structure, stability, permanence. Black holes are part of that. They're not threats, they're just features of the cosmos, like mountains on Earth. They exist, they shape their surroundings, and they remind us that the universe is vast, complex, and full of wonders we're still learning to understand. And as you sleep tonight, those black holes are out there, warping space, holding galaxies, silent and steadfast in the cosmic night. The universe is expanding. This might be one of the most profound discoveries in all of science. It means that space itself is growing, becoming larger over time. Galaxies are moving apart from each other, not because they're traveling through space, but because the space between them is increasing. It's as if the universe is a balloon being inflated, and galaxies are dots on the surface. As the balloon expands, the dots move apart, even though they're not moving across the surface. This expansion was discovered in the 1920s by astronomer Edwin Hubble. He observed that distant galaxies were moving away from us, and the farther away they were, the faster they were receding. This relationship, now called Hubble's law, showed that the universe was not static, but dynamic, constantly changing. Before this discovery, most scientists assumed the universe was eternal and unchanging. Hubble's observations changed everything. If the universe is expanding now, it must have been smaller in the past. If you could run time backward, you'd see galaxies getting closer together, space shrinking. Eventually, you'd reach a point where all matter and energy was compressed into an incredibly hot, dense state. This is what we call the Big Bang, the beginning of the universe as we know it. The Big Bang wasn't an explosion in space, it was an expansion of space itself, starting from a hot, dense state about 13.8 billion years ago. The expansion of the universe doesn't mean that everything is getting larger. Atoms don't expand. You don't expand. Planets and stars don't expand. Even galaxies don't expand. Gravity holds these structures together against the expansion. It's only on the largest scales, between clusters of galaxies, that the expansion is noticeable. On smaller scales, gravity dominates, keeping things bound together. The rate of expansion is described by something called the Hubble constant. This number tells us how fast the universe is expanding. Currently, it's about 70 kilometers per second per megaparsec. That means for every megaparsec of distance, about 3.26 million light years. The expansion causes objects to move apart at 70 kilometers per second. This might sound fast, but given the enormous distances involved, the expansion is actually quite gentle. What's driving this expansion? That's one of the biggest questions in cosmology. In the early universe, the expansion was driven by the energy released during the Big Bang. As the universe expanded and cooled, gravity should have slowed the expansion down, perhaps even reversing it eventually. But in the late 1990s, astronomers discovered something surprising. The expansion is accelerating. It's speeding up, not slowing down. This acceleration is attributed to dark energy, a mysterious form of energy that permeates all of space. Dark energy makes up about 68% of the universe, but we don't know what it is. It doesn't interact with matter or light in any way we can detect, except through its gravitational effects. Dark energy has a repulsive effect, pushing space apart, causing the expansion to accelerate. It's one of the greatest mysteries in modern science. Because of dark energy, the universe's expansion will continue forever. Galaxies will drift farther and farther apart. Eventually, galaxies outside our local group will be so far away that their light can no longer reach us. The universe will become a lonelier place with fewer and fewer galaxies visible in the sky. Trillions of years from now, observers in the Milky Way might see only their own galaxy and perhaps a few others nearby. The rest of the universe will have receded beyond the horizon. But that's far in the future. For now, the universe is still rich with galaxies, still full of light and structure. The expansion is happening, but it's slow enough that we can still see distant galaxies, study them, learn from them. We're living in an era when the universe is observable, when we can look out and see billions of years of cosmic history. It's a privilege, in a way, to exist at a time when the universe is so rich and visible. The expansion also affects the light from distant galaxies. As space expands, it stretches the light traveling through it, shifting it toward longer wavelengths. This is called redshift. The farther away a galaxy is, the more its light is redshifted. By measuring redshift, astronomers can determine how far away a galaxy is and how fast it's moving away from us. Redshift is one of the most important tools in cosmology, allowing us to map the universe and study its history. There's something calming about the expansion of the universe. It's happening on such vast scales, so slowly from our perspective, that it doesn't affect daily life at all. You can't feel the expansion. You can't see it without powerful telescopes and careful measurements. It's a background process, something the universe is doing quietly, steadily, all the time. It's been expanding for 13.8 billion years, and it will keep expanding for trillions more. The expansion also tells us that the universe had a beginning. Time itself started with the Big Bang. Before that, there was no before. It's hard to wrap your mind around, but the universe hasn't existed forever. It had a starting point, a moment when it came into being. Everything we see, all matter and energy, all space and time, originated from that hot, dense planets state 13.8 billion years ago. Some people find this unsettling. The idea that the universe had a beginning and will have an end, at least in terms of being interesting and full of life. But there's also something peaceful about it. The universe has a story, a narrative with a beginning, a middle, and an end. We're part of that story, living in the middle chapters when stars are still shining, galaxies still forming, life still possible. It's a good time to be alive, in cosmic terms. The expansion of the universe also means that the cosmos is much larger than we can observe. Light from the most distant galaxies has been traveling for over 13 billion years, but because the universe has been expanding all that time, those galaxies are now much farther away than 13 billion light years. The observable universe is about 93 billion light years across, but the entire universe is likely much, much larger, perhaps infinite. We'll never know for sure because we can only see the part of the universe whose light has had time to reach us. This means there are galaxies, stars, planets that we'll never see. They're too far away, and the light from them hasn't had time to reach us yet. Perhaps it never will if the expansion continues to accelerate. There's a horizon beyond which we can't see, a limit to our knowledge. But that's okay. We have plenty to study within our observable universe, billions of galaxies, each one full of stars, each star potentially surrounded by planets. As you lie here, drifting toward sleep, you might imagine the universe expanding around you. Space is growing, stretching, creating more room. But you're not being stretched. You're held together by the forces that bind atoms, by the gravity that keeps you on Earth. The expansion is happening on scales far larger than you, far larger than Earth or the solar system. It's a cosmic process, gentle and unstoppable. There's comfort in the idea that the universe is making room, expanding to accommodate everything. There's no crowding, no pressure, just endless space, growing larger all the time, giving every galaxy, every star, every planet room to exist. You're part of that universe, part of that expansion, and as the universe grows, it carries you with it on a journey through time and space that began nearly 14 billion years ago and will continue for trillions of years to come. Let the expansion be a metaphor for rest, just as the universe is making more space. You can make more space in your mind, letting go of thoughts, letting go of worries. There's room for everything in the universe, and there's room for everything in your mind too. You don't have to hold onto anything. You can just let it drift away, like galaxies receding into the cosmic night, carried by the gentle, inexorable expansion of space itself. Rest in that expansion. Rest in the knowledge that the universe is patient, that it takes its time, that it's been growing for billions of years and will keep growing. There's no rush, no deadline, just the steady, eternal increase of space, creating room for stars, for planets, for life, for you. And as you drift into sleep, you're part of that process, part of the universe's gentle unfolding, carried along by forces beyond your control. Safe in the knowledge that the cosmos has room for everything, including your need for deep, peaceful rest. Moons are some of the most peaceful objects in the solar system. They orbit planets, following elliptical paths that they've traced billions of times. Our own moon has been orbiting Earth for over 4 billion years, always showing us the same face, locked in place by tidal forces. It rises and sets with predictable regularity, marking the passage of time with its phases, from new to crescent, to full and back again. The moon is Earth's constant companion. It's been there through all of Earth's history, through the age of dinosaurs, through the ice ages, through the rise of humanity. It's seen everything that's happened on our planet, silently orbiting, reflecting the sun's light down to us. In its own way, the moon is timeless, unchanging, a reliable presence in our night sky. Other planets have moons too, some many more than we do. Jupiter has at least 79 known moons. Saturn has 82. Uranus has 27. And Neptune has 14. These moons vary enormously in size and character. Some are large, almost planet-sized, Others are tiny, just a few kilometers across. Some are rocky, some icy. Some have atmospheres, some are bare. Each one is unique, with its own geology, its own history. Jupiter's moon Europa is one of the most interesting. It's covered in ice, smooth and bright, crisscrossed with cracks and ridges. Beneath that ice is believed to be an ocean, kept liquid by the tidal heating from Jupiter's powerful gravity. This ocean might be tens or even hundreds of kilometers deep, containing more water than all of Earth's oceans combined. And in that dark, cold ocean, there might be life. We don't know yet, but it's a tantalizing possibility. Another of Jupiter's moons, Io, is the most volcanically active body in the solar system. It's constantly being squeezed and stretched by Jupiter's gravity, which generates heat in its interior. This heat drives hundreds of active volcanoes, which erupt constantly, spewing sulfur and other materials into space. Io's surface is young, constantly being renewed by volcanic activity. It's a violent, dynamic place, very different from our quiet moon. Saturn's largest moon, Titan, is another fascinating world. It's the only moon in the solar system with a thick atmosphere, thicker even than Earth's. Titan's atmosphere is mostly nitrogen, like Earth's, but it's much colder. The surface temperature is about minus 180 degrees Celsius. At that temperature, methane and ethane, which are gases on Earth, exist as liquids. Titan has lakes and rivers of liquid methane, and it even has weather, with methane rain falling from clouds. Titan is shrouded in a thick orange haze, which makes it difficult to see the surface. But spacecraft have used radar to map the moon, revealing a landscape with dunes, mountains, and vast plains. There are lakes near the poles, filled with liquid hydrocarbons. It's a strange, alien world, yet in some ways familiar. Like Earth, it has weather, erosion, seasonal changes. It's a world where rain falls and rivers flow, just not with water. Saturn's moon, Enceladus, is smaller, but equally intriguing. It has geysers near its south pole that shoot water ice and vapor into space. These geysers are fed by an ocean beneath the ice, similar to Europa. The water from these geysers forms a ring around Saturn, and spacecraft have flown through the plumes, analyzing the chemistry. The water contains organic molecules, salts, and other compounds that suggest the ocean might be habitable. Like Europa, Enceladus is a place where life might exist. Neptune's largest moon, Triton, is unusual because it orbits backward in the opposite direction to Neptune's rotation. This suggests that Triton didn't form with Neptune, but was captured, pulled into orbit by the planet's gravity. Triton is geologically active, with geysers that spew nitrogen gas and dark material into the thin atmosphere. The moon's surface is young, with few craters, indicating that it's been resurfaced relatively recently by geological processes. Our own moon is tidally locked to Earth, meaning the same side always faces us. This happened because Earth's gravity created tidal bulges on the moon, which acted like brakes, slowing the moon's rotation until it matched its orbital period. Most large moons in the solar system are tidally locked to their planets. It's a natural result of being close to a much larger body. The process takes millions of years, but eventually the moon's rotation synchronizes with its orbit. From the moon's surface, Earth would appear to hang in the same spot in the sky, never rising or setting. It would go through phases, just like the moon does for us, waxing from new Earth to full Earth and back. The Earth would appear much larger than the moon does from Earth, about 4 times wider. A beautiful blue and white marble hanging in the black sky. Half of the moon never sees Earth at all. The far side of the moon looks out into space, with only stars and distant planets visible. The moon's surface is ancient, heavily cratered from billions of years of impacts, without an atmosphere to protect it. Every meteorite that approaches strikes the surface, creating craters large and small. The largest impacts created vast basins that filled with lava billions of years ago, forming the dark patches we see as the man in the moon. or the rabbit, depending on cultural interpretation. These dark areas, called Maria or seas, are actually ancient lava flows, now solid and cold. Walking on the moon would be a quiet experience. There's no air, so there's no sound except what you could hear through your spacesuit. Your footsteps would be silent. The sky would be black, even during the day, because there's no atmosphere to scatter light. The sun would be a brilliant white disk, harsh and unfiltered. Stars would be visible even in daylight, scattered across the black sky. It would be beautiful in a stark, otherworldly way. The moon affects Earth in important ways. Its gravity creates tides in our oceans, pulling the water toward it as it orbits. The sun's gravity creates tides too, but the moon's effect is stronger because it's closer. When the moon and sun align during new and full moons, their tidal effects combine, creating especially high and low tides called spring tides. When they're at right angles during quarter moons, the tides are less extreme, called neap tides. The moon also stabilizes Earth's rotation. Without it, Earth's tilt would vary much more over time, causing dramatic climate shifts. The moon's presence keeps Earth's axis relatively stable, which has been important for the development of stable climates and perhaps for the evolution of complex life. The moon is more than just a satellite. It's been a partner to Earth throughout our planet's history, shaping our world in subtle but important ways. Moons throughout the solar system follow their orbits with the same patient regularity as our moon. They're locked in gravitational dances with their planets, some orbiting in days, others in weeks or months. Some moons orbit so close to their planets that tidal forces are tearing them apart, creating rings of debris. Others orbit far away, barely held by their planet's gravity, taking years to complete a single orbit. As you rest here tonight, you might imagine standing on a distant moon, looking up at the giant planet it orbits. Perhaps you're on Europa, with Jupiter filling half the sky, its bands of clouds slowly churning. Its great red spot, a massive storm larger than Earth. The your feet glows faintly in Jupiter's reflected light. The sky is full of stars, and in the distance, you can see other moons, small points of light moving slowly against the background of space. Or perhaps you're on our moon, in the sea of tranquility where Apollo 11 landed. The Earth hangs in the black sky above you, blue and white and beautiful. You can see the continents, the oceans, clouds swirling in patterns. It's the only color in the sky, the only break from the black and white of the lunar landscape, and it's silent, profoundly silent, the most peaceful silence you've ever experienced. Moons are witnesses to the solar system's history. They've been orbiting their planets for billions of years, seeing everything, recording impacts on their surfaces, preserving evidence of the solar system's violent past. They're timekeepers, marking the passage of days and months with their regular motions. They're companions to their planets, bound by gravity, following paths that have been carved out over eons. Let the quiet orbits of moons lull you toward sleep. Imagine the moon rising outside your window, following its ancient path across the sky. It's been rising and setting every day of your life, every day of every human life throughout history. It's reliable, constant, predictable. And tonight, as you drift into sleep, the moon continues its orbit, pulling the tides, reflecting sunlight, keeping Earth company in the darkness of space. You can rest knowing that the moon will be there tomorrow and the day after, and for billions of years to come. A gentle presence in our sky, a reminder that some things endure, that some patterns never change, that the cosmos maintains its rhythms, quiet and eternal, while you sleep peacefully below. Comets and asteroids are ancient wanderers, remnants from the formation of the solar system. They've been drifting through space for over 4.5 billion years, following their orbits, mostly unchanged since the solar system was young. These small bodies are like time capsules, preserving material from the early days when planets were still forming, when the sun was newly born and the solar system was still finding its shape. Asteroids are rocky bodies, most of them orbiting the sun in a region between Mars and Jupiter called the asteroid belt. There are millions of asteroids in this belt, ranging in size from tiny pebbles to Ceres, which is large enough to be classified as a dwarf planet despite their numbers. The asteroid belt is mostly empty space. If you were to fly through it, you probably wouldn't see any asteroids at all. They're spread out over such a vast volume that they rarely come close to each other. Each asteroid follows its own orbit around the Sun, taking years to complete a single revolution. They tumble slowly as they move, rotating end over end in the silence of space. Some asteroids are solid chunks of rock or metal. Others are loose collections of rubble, barely held together by their own weak gravity. They're called rubble piles, and if you could stand on one, you'd barely feel any gravity at all. You could jump and drift away into space. Asteroids are leftover building blocks from planet formation. When the solar system was young, countless small bodies like these collided and stuck together, gradually building up into larger objects. In the inner solar system, these collisions eventually formed the rocky planets: Mercury, Venus, Earth, and Mars. But in the asteroid belt, Jupiter's powerful gravity prevented the asteroids from coming together to form a planet. Instead, they remain scattered, a planet that never was. Some asteroids have been visited by spacecraft. We've seen their surfaces up close, cratered and ancient, bearing the scars of billions of years of impacts. Some are gray, some are reddish, some almost metallic. Each one tells a story about the early solar system, about the conditions that existed when they formed. Scientists study asteroids to learn about our origins, about the material that came together to form Earth and the other planets. Comets are different from asteroids. They come from the outer reaches of the solar system, from two vast regions: the Kuiper Belt beyond Neptune, and the Oort cloud, which extends halfway to the nearest star. Comets are mixtures of ice and rock, sometimes called dirty snowballs. They spend most of their time in the cold darkness of the outer solar system, frozen and dormant, moving in their distant orbits, but sometimes a comet's orbit brings it close to the sun. As it approaches, the sun's heat begins to warm the comet's surface. The ice starts to sublimate, turning directly from solid to gas without becoming liquid. This gas, along with dust particles, streams away from the comet, forming a glowing cloud called a coma, and a long tail that can stretch for millions of kilometers. The tail always points away from the sun, blown by the solar wind. That stream of particles constantly flowing outward from the sun. Comets are beautiful, ethereal objects. Ancient peoples saw them as omens, signs in the sky. But they're just small bodies following their orbits, made visible when they pass close enough to the sun. Some comets return regularly. Halley's Comet, for example, orbits the sun once every 76 years. It's been observed for thousands of years, recorded by astronomers throughout history. The last time it passed close to Earth was in 1986. It will return in 2061. Other comets visit the inner solar system only once. They come from the Oort cloud on orbits that take millions of years to complete. They swing past the sun once, developing their spectacular tails, and then head back out into the darkness, not to return for millennia, or perhaps never. These long-period comets are travelers from the distant edge of the solar system, bringing us samples of material that has remained frozen and unchanged since the solar system's birth. The Oort cloud is a vast, spherical shell of icy bodies surrounding the solar system. It extends from about 2,000 times Earth's distance from the sun out to nearly 100,000 times that distance. That's almost a quarter of the way to the nearest star. The Oort cloud contains trillions of comets, most of them too far away and too small to ever be seen. They drift in the darkness, barely moving, barely held by the sun's weak gravity at that distance. Occasionally, something disturbs an Oort cloud comet. Perhaps a passing star's gravity gives it a nudge. Perhaps the gravitational influence of the galaxy itself shifts its orbit slightly. Whatever the cause, the comet begins falling toward the inner solar system, accelerating as it gets closer to the sun. Years or centuries later, it appears in our sky, a new comet, never before seen by human eyes. The Kuiper belt is closer than the Oort cloud, beginning just beyond Neptune's orbit. It's home to countless icy bodies, including several dwarf planets like Pluto, Haumea, and Makemake. These are worlds on the edge of the solar system, cold and distant, where the sun appears as just a bright star in the black sky. Short-period comets, those with orbits less than 200 years, generally come from the Kuiper belt. There's something peaceful about imagining these small bodies drifting through space. They follow their orbits without thought, without purpose, simply moving as gravity dictates. An asteroid might orbit the sun 1 billion times over the age of the solar system, following the same path again and again, patient and unhurried. A comet might spend millions of years in the outer darkness, slowly moving along its enormous orbit, until finally it makes its brief, spectacular visit to the inner solar system. These objects remind us that the solar system is vast, that there's much more to it than just the planets. Beyond Neptune, beyond Pluto, there's still more solar system, stretching out to incredible distances, and all of it is in motion, all of it orbiting the sun, held by gravity across billions of kilometers of space. It's a reminder of the sun's reach, of how far its influence extends. Asteroids and comets also connect us to the past. The material they're made of is ancient, pristine, largely unchanged since the solar system formed. Some of that material came from previous generations of stars, from supernovae that exploded before the sun existed. The atoms in asteroids and comets have been on a long journey, from stars to interstellar clouds to the solar nebula to these small bodies. And sometimes that material reaches Earth in the form of meteorites. Meteorites are pieces of asteroids or comets that survive passage through Earth's atmosphere and land on the surface. They're fragments of the early solar system, delivered to us from space Scientists treasure meteorites because they provide direct samples of these ancient bodies. By studying them, we can learn about conditions in the early solar system, about the chemistry of planet formation, about the age of the sun and planets. As you rest here tonight, you might imagine a comet in the outer solar system, barely moving in its distant orbit. The sun is just a point of light, bright but distant, providing almost no warmth. The comet is frozen, silent, alone in the darkness. It's been traveling this orbit for millions of years, and it will continue for millions more. There's no hurry, no destination, just the slow, eternal circuit through the outer solar system, patient and peaceful. Or imagine an asteroid tumbling slowly through the asteroid belt. It's been following this same orbit for billions of years, since before Earth had continents, before life emerged from the oceans, before the moon's surface cooled. The asteroid has no awareness, no sense of time passing. It just exists, moving through space, a small piece of rock in the vast cosmic machine. And that's enough. It doesn't need to be anything more. These objects teach us patience. They've been following their orbits for so long, moving so slowly that human timescales seem like nothing in comparison. We live our entire lives in the blink of an eye compared to the age of an asteroid. Yet the asteroid doesn't measure time. It doesn't count its orbits. It simply is moving through space, part of the solar system, part of the universe. Let that patience flow into you as you drift toward sleep. There's no need to count the hours, no need to measure time. Just like comets and asteroids, you can simply exist in this moment, moving through time without effort, without thought. Your body knows how to sleep, just as asteroids know how to orbit. You don't have to do anything. Just let go, let time pass. Let yourself drift through the night like a comet through the outer darkness, peaceful and unhurried. The solar system is full of these wanderers, these ancient bodies that have seen everything, been everywhere in their orbits, and yet remain unchanged. They're constants in a changing universe, reliable, predictable, following the same paths over and over. And tonight, as you sleep, they're still out there, still orbiting, still drifting through space, companions in the cosmic night, moving through the darkness with the same patience and peace that can carry you into deep, restorative sleep. The universe operates on cycles, great rhythms that span millions, billions, even trillions of years. These cycles are so slow, so vast, that we can barely perceive them, yet they're fundamental to how the cosmos works, how it renews itself, how it maintains balance over incomprehensible stretches of time. Understanding these cycles helps us see the universe not as a static place, but as something alive in its own way, constantly changing, yet also constant in its patterns. Stars have cycles. They're born, they live, they die, and their material is recycled into new stars. A star begins as a cloud of gas, collapses under gravity, ignites fusion in its core, and shines for millions or billions of years. When its fuel is exhausted, it dies, either gently shedding its outer layers or exploding in a supernova. The material it releases mixes with the interstellar medium, enriched with heavier elements forged in the star's core. Eventually, that material becomes part of a new gas cloud, which collapses to form new stars. The cycle continues. Our sun is part of this cycle. It formed about 4.6 billion years ago from a cloud of gas and dust that contained material from earlier generations of stars. Some of the atoms in the sun and in Earth were once part of stars that lived and died before our solar system existed. In about 5 billion years, the sun will exhaust its hydrogen fuel and begin to die. It will swell into a red giant, perhaps engulfing the inner planets. Eventually, it will shed its outer layers, forming a planetary nebula, and the core will become a white dwarf, slowly cooling over trillions of years. But even after the sun dies, its atoms will remain. They'll drift through space, perhaps becoming part of a new gas cloud, a new star, a new planet. The cycle will continue. Nothing is truly lost in the universe. everything is recycled, transformed, given new form. It's a kind of cosmic conservation, a principle that matter persists, changing but never disappearing. Galaxies have cycles too. They rotate, their stars orbiting the galactic center over millions of years. They consume smaller galaxies, growing over time. They form new stars from their reservoirs of gas, converting that gas into stellar light. When those stars die, some of their gas is returned to the galaxy, ready to form new stars. This cycle of star formation and death continues for billions of years, slowly consuming the galaxy's gas supply. Eventually, a galaxy runs out of gas. Star formation slows, then stops. The galaxy becomes full of old, red stars, slowly fading as their fuel runs out. This process takes an incredibly long time. Spiral galaxies like the Milky Way will continue forming stars for many billions of years. But eventually, even the Milky Way will exhaust its gas, and the era of star formation will end. The galaxy will become quiet, dark, full of stellar remnants, white dwarfs, neutron stars, black holes. Even planets have cycles, though they're different from stars. Planets don't die, but they change. Earth has gone through many cycles in its history. Continents have formed and broken apart multiple times. Oceans have risen and fallen. Ice ages have come and gone. Life has emerged, evolved, experienced mass extinctions, and recovered. Through all of this, Earth has persisted, orbiting the sun, spinning on its axis, maintaining the cycles that make it a living world. The water cycle on Earth is a beautiful example of cosmic cycling on a planetary scale. Water evaporates from the oceans, forms clouds, falls as rain, flows through rivers back to the sea. This cycle has been operating for billions of years. Some of the water you drink might have fallen as rain on ancient forests, might have been part of the ocean when dinosaurs lived, might have been ice during the last ice age. Water is recycled, used over and over, never consumed, just moving through the cycle. The carbon cycle is another example. Carbon atoms move from the atmosphere into plants through photosynthesis, from plants into animals that eat them, from animals back into the atmosphere when they breathe or decay. Carbon is stored in the ground as fossil fuels released by volcanoes, dissolved in the oceans. The cycle is complex, but it's been operating throughout Earth's history, maintaining the balance of carbon in different reservoirs. These cycles remind us that nothing is permanent in its current form. Everything changes, but the changes follow patterns. Atoms move from stars to space to new stars. Water moves from ocean to sky to land to ocean. Carbon moves through living things and the atmosphere and the ground. The cycles operate at different speeds, but they all share the quality of returning, of repeating, of maintaining continuity, even as individual forms change. The universe itself may be part of a cycle, though this is more speculative. The universe began with the Big Bang about 13.8 billion years ago. It's been expanding ever since, and that expansion is accelerating. Current understanding suggests the universe will expand forever, growing colder and darker as stars die and are not replaced. Trillions of years from now, the universe will be a very different place, dominated by black holes and the faint radiation they emit as they slowly evaporate. But some theories suggest the universe might not expand forever. Perhaps dark energy will change, causing the expansion to slow and reverse. The universe would then begin to contract, galaxies coming closer together, space shrinking, until everything collapses back into a hot, dense state. This is called the Big Crunch. And perhaps after the Big Crunch, there could be another Big Bang, starting a new cycle. The universe might expand and contract over and over, each cycle lasting trillions of years. We don't know if this is true. Current evidence suggests the universe will expand forever, not contract. But the idea of cosmic cycles is appealing. It suggests that even the universe itself follows patterns, that there's a rhythm to existence at the largest scales, whether or not the universe cycles. It's clear that cycles are fundamental to how the cosmos cosmos operates. From the rotation of planets to the life cycles of stars, to the formation and evolution of galaxies, everything moves in patterns, rhythms, cycles. These cycles are comforting in a way. They tell us that change is natural, that nothing stays the same, but also that there's continuity, that patterns persist. The sun will die one day, but other stars will be born. Our galaxy will run out of gas eventually, but it's been forming stars for billions of years and will continue for billions more. The cycles operate on timescales so long that they're effectively eternal from our perspective. As you lie here, breathing slowly, you're part of cycles too. Your breath is a cycle, in and out, bringing oxygen to your cells and removing carbon dioxide. Your heartbeat is a cycle, pumping blood through your body. Your sleep cycle brings you from wakefulness through light sleep to deep sleep and back again, multiple times through the night. You're a collection of cycles operating at different speeds, all working together to keep you alive. Even your place in the universe is part of a cycle. You're made of atoms that were forged in stars, atoms that have been part of many things before you and will be part of many things after you. You're borrowing these atoms for a while, arranging them in the pattern that makes you who you are. Eventually, you'll return them to the universe, and they'll continue their journey, becoming part of other cycles, other patterns, other forms. There's peace in understanding that you're part of these great rhythms, these cosmic cycles. You're not separate from the universe. You're part of it, subject to the same laws, following the same patterns. Your life is a cycle too, with a beginning, a middle, and an end. And that's okay. That's how the universe works. Everything cycles, everything changes, everything transforms. And in that constant transformation, there's a kind of permanence. The patterns persist even as individuals come and go. Let the thought of cycles calm you as you drift toward sleep. Let the rhythm of your breath mirror the rhythm of the cosmos. Breathe in, breathe out. Stars are born, stars die. Galaxies form, galaxies fade. The universe expands, and perhaps one day it will contract. Everything is moving, cycling, following patterns that have existed for billions of years and will continue for billions more. And you're part of that. You're part of the great cosmic dance, the endless cycling of matter and energy through space and time. Rest in the knowledge that cycles continue, that patterns persist, that the universe maintains itself through constant change. Nothing stays the same, but nothing is lost. Everything just transforms, moves through cycles, takes new forms. And tonight, as you sleep, you're moving through your own cycle, from wakefulness to dreams to deep sleep. It's natural, it's necessary, it's part of the rhythm of life. So let yourself go. Let yourself move through the cycle, trusting that your body knows what to do, that it's been doing this every night of your life, following its own rhythm, its own pattern, its own place in the great cycles of existence. The cycles of the cosmos are patient, eternal, unhurried. They don't rush. They take the time they need, following patterns that have been established since the beginning. And you can be patient too. You can take the time you need to rest, to sleep, to let your body and mind recover. There's no hurry. The cycles will continue. The universe will keep turning. And you can simply rest, part of the pattern, part of the rhythm, part of the great cosmic cycle that connects all things across space and time. And so we come to the end of our gentle journey through space and the universe. We've drifted through the darkness between stars, bathed in ancient light, watched galaxies move through the cosmic night. We've witnessed the birth of stars in glowing nebulae, felt the gentle pull of gravity, and imagined planets orbiting distant suns beneath alien skies. We've wrapped ourselves in the cosmic microwave background, that faint echo of the universe's beginning. We've contemplated black holes and their warping of space and time. We've felt the expansion of the universe, creating more room, more space, endlessly growing. We've orbited with moons in their quiet paths, drifted with comets and asteroids through timeless space, and recognized ourselves as part of the great cycles that govern everything. The universe is vast beyond imagination, ancient beyond comprehension, and yet it follows simple, elegant rules. Gravity, light, motion, cycles. Everything is connected, from the smallest atom to the largest galaxy, and you are part of that connection, made of star stuff, following cosmic rhythms, orbiting through space on this small planet we call home. As you rest now, or perhaps you've already drifted into sleep, know that the universe continues around you. Stars are shining. Galaxies are turning. Space is expanding. Comets are drifting through the outer darkness. And all of it is peaceful, patient, following patterns that have existed for billions of years. The cosmos doesn't rush, doesn't worry, doesn't hurry. It simply exists, vast and calm, holding everything within it, including you. Sleep well, knowing you're part of something infinite and beautiful. Let the quiet darkness of space cradle you. Let the ancient light of stars guide you into dreams, and rest in the gentle embrace of the universe, which has been here long before you and will continue long after, eternal and peaceful, a cosmic ocean in which we all drift together. Good night, and thank you for exploring space and the universe with Sleepy Facts with Justin. May your dreams be as vast and peaceful as the cosmos itself.